Hello friend, how are you? I'm fine. I hope you are will be fine. Thank you very much. Let's start today topic. Today our lecture is lecture number 3 of crystal field theory CFT. Today we will explain application of CFT crystal field theory. Application of crystal field theory. There are few application of crystal field theory. If crystal field theory can be applicable, crystal field theory can be applicable to crystal field theory can be applicable to octahedral complexes octahedral complexes as well as it can be applicable to tetrahedral complexes. It can also applicable to tetragonal complexes. Here is one term we will explain in separate video called Jahn-Taylor distortion. Tetragonal complexes is due to Jahn-Taylor distortion. But sorry, in fourth one case is that is application of CFT crystal field theory. This is square planar complexes. The fourth one application is square planar complexes. Crystal field theory can be applicable to octahedral complexes, tetrahedral complexes, tetragonal complexes, and square planar complexes. In octahedral complexes, there is coordination number in octahedral complexes will be 6, in tetrahedral complexes will be 4, in tetragonal complexes will be 6, and square planar complexes will be 4. So is it clear? So according to sequence, first of all I will explain octahedral complexes, and today video and today lecture I will explain the one of the application of crystal field theory as octahedral complexes. So today our topic is octahedral complexes. In octahedral complexes, how crystal field theory can be applicable. Let's suppose there is one ligand. Let's suppose there is central metal atom M plus N. There is central metal atom here. I already told you that in octahedral complexes, central metal atom should have 6 coordination number. So there should be 6 ligand. So this is ligand first, this is ligand 2, this is ligand third, this is ligand fourth, this is ligand 5, this is ligand 6. So these all are with the coordination, these all are with attraction to the central metal atom. These 4 are in square planar, these 4 are in xy plane, and the other one is in one is above the plane and the other one is below the plane. Like let's suppose that let's suppose this is xy plane, that is xy plane. Let's suppose that is the blue is x-axis, the green is x-axis, while the white is y-axis, and that is z-axis. So let's suppose L is here, this one L is here, this one L is here, this one L is here. So there are 4 ligand, while the other one is here. Or you can say also say that the one ligand is here, one ligand is here, one ligand is here, one ligand is here. These are four. These are in square planar. These are in square planar. That is square and planar in one plane. So if that is one is the above plane and the other is let's suppose one ligand is here and one ligand is here. So these all are interaction with different, yeah. So here if you can say that this is the one face of this geometry, this is the another face, this is the another face, this is another face. So that is one face, this is second face, this is third face, this is fourth face. Similarly that is five face, that is six face, that is seven face, and this is eight face. So here is eight face, and we know that octa means eight, octa means eight, while hedral hedral while hedron mean face, means here is eight faces, like that. So how the geometry, how crystal field theory involved in this shape, in this geometry, sorry. There is six interaction in this complex, in octahedral complexes. There is six ligand interaction, there is a six ligand interaction, six ligands interaction. There is six ligand interaction with central metal atom, CMA, central metal atom. CMA denoted for, stand for central metal atom. There is six ligand interaction with central metal atom. Among these six ligand, four ligands approaching to central metal atom in a xy plane. Four ligands are in xy plane, that is x plane, that is let's suppose that is x plane, that is y plane, let's suppose this is z plane, and two ligands approaching to the central metal atom, in a z plane. Means four ligands are approaching to the central metal atom in xy plane. There are two ligands in x plane, two ligands in y plane, and two ligands in z plane. Total in xy plane and square plane it is four ligands, and z plane it is approaching through the central metal two ligands. So here some distortion occur, like how. So you can also screenshot it, sorry. Z ligand approaching to the central metal atom and z plane. You can also take screenshot from this. I am now just going to remove to clear the board. So the board is yeah, the board is now cleared, very clear. So how the interaction occur, how crystal field theory is involved in this system. I already told you that the d orbitals of central metal atom are exposed to make or to take part in interaction with ligands, with six different ligands. In case of octahedral complexes, in six ligands. That is the case of application of octahedral complexes. Ligand field theory, crystal field theory are applying. We are applying crystal field theory to octahedral complexes. D orbitals of central metal atom are exposed to take part in interaction with six different ligands or six similar ligands. So we already know that the d orbitals have d orbitals have 5 degenerate orbital, 5 degenerate orbital 5 degenerate orbital. Here one of my friend he he was told me that, and my class he was told me that in octahedral complexes there was 5 degenerate orbital and d orbitals, and the ligands are 6 ligands. So here is one ligand are excess in amount, are the one orbital of d orbital are less efficient to the system, because these are not in equal in number. I told you when I was explaining that, so he his concept will be, was cleared. So the same problem I am also telling you, I am also clarified you. D orbital have 5 degenerate orbital. These 5 degenerate orbital are dxy, dxz, dyz, dx square minus y square, and dz square. These 5 degenerate orbital. Among these 3 orbitals are called T2G orbital, while these two orbitals are called EG orbital. I already told you that these orbital are lying on x-axis, on axis. These orbital are lying in between axes. So is it clear? So in this case octahedral complexes, let's suppose this is the central metal atom, this is the central metal atom which is in plus in charge, where it is the oxidation state of the central metal atom. So let's suppose that is the one ligand, that is another ligand, that is another ligand, that is another ligand. This is x-axis, this is y-axis, this is y-axis, this is x-axis. So let's suppose the z-axis, one is the out of the board and one is the inside of the board. That one ligand will be approaching from the inside of the board toward the metal atom, and one will be from the outside of the board to the central metal atom approaches. So let's imaginary that that is z-axis, that the above part, this part is the outside of the plate and that is inside plane, like that. So that is one ligand will be approaching from here and one ligand will be approaching from here, that is on z-axis, like that. I already told you that the T2G orbital, the EG orbital lying that are lying on axis, like that. These orbitals that lying on axis, EG orbital, one EG orbital, the dx square minus y square will be like that. That is one lobe, one dumbbell, then that is another lobe, make another dumbbell. I mean it means that this is one lobe, this is another lobe, one dumbbell, two dumbbell. That means that dx square minus y square orbital formed, that is dumbbell shape, and there is double dumbbell shape. So these are dx square minus y square, while one and the z square, dz square orbital, dz square orbital will be show like that, that is on z axis, and will be circulate on this. Before this lecture, in lecture number 2, I was explained you clearly that how is the shape of EG and T2G orbital. So you can also search on YouTube that the second lecture of CFT, lecture number 2 on crystal field theory. So here is that clear? So let's suppose when ligand approaches to when ligand approaches along x-axis, along y-axis, and along z-axis in xy coordination, in xyz coordination. So you can say that you can clearly watching that the interaction of ligand with the EG set orbital, it is very effective overlapping, effective interaction, sorry, not overlapping, effective interaction take place, because ligand are head to head interaction here is present, that is ligand, while the orbital, the lobes of the the lobes of the EG set of orbital are on the way that ligand approaches the same way. So in this case, the EG set orbital increased, energy increased, increased. Why it is increased? It is increased because it was increased because the interaction, because effective effective interaction take place, because effective interaction is present, effective interaction is present, or head to head interaction is present here. So ligand will approaches the energy of the set EG set orbital will have energy increased, means dx or minus 5 and d square energy will increase. It means that the degeneracy of d orbital there, where five different orbital that all are degenerate orbital, the degeneracy of these d orbital will be remain cannot be remains, will be dissociated, will be split up. While the T2G set energy, it will become decreased, the EG set energy increased, the T2G set energy decreased. Why it is decreased? It is decreased because the energy of these orbital are lying in between axes. I already told you that how the T2G set orbital are present. So that is like, that is x-axis, that is y-axis, that is z-axis, the red pen is z-axis, green pen is y-axis, the green pen is x-axis, while white pen is y-axis. So and that is y, that is x. So the xy orbital will be like here, while the xz will be here, dxz will be here, that is x, that is z, xz will be here, while yz dyz will be here, that is y, that is z, one will lobe here, one lobe here. So it will be like that. So if the ligand will approaching in these different way, so the T to G orbital, these all are in between the axes, so their interaction will be very less with ligands. So that's why their energy is decreased, while the interaction of EG is more. So that's why EG sets of orbital will EG sets of d orbital will be energy increased. Is it clear that the T to G set orbital have energy decreased, while the EG set energy is increased? I think it will be clear. I hope you will be understand very clearly. So you can take also screenshot. You can also take screenshot. So now I am going to clear the board. So let's see that what the d orbital, that is d orbital of the central metal atom, that in this d orbital and d orbital there has 5 degenerate orbital, all have same energy and same shape, same symmetry, same energy, same shapes. That is dxy, dxz, dyz, dx square minus y square, dz square. These all are these 5 orbitals. Yeah, these are 5 orbitals. So I told you, I explained you that that is d orbital. These all are degenerate orbital, degenerate orbital, degenerate degenerate orbitals. These all are degenerate orbitals. These all have same energy and same symmetry, same energy, same shape, because these are degenerate orbitals. So here I already told you, when the ligand approaches in xy plane, when the ligand approaches in sex ligand in xy plane, the energy of T2G, that is EG sets, that is T2G sets, the energy of EG set, that is in EG set, there is dx square minus y square and dz square, dx square minus y square and dz square. This energy will be increased from normal, and the T to G energy will be decreased, that is dxy, dxz, dyz. Their energy will be decreased, while the energy of dx square minus y square will be increased. Why it is increased? Because it is lying on x-axis, so the ligand will effectively interact with them, so their energy will be increased, while that is not effectively interaction, so their energy will be decreased from normal. But so let's suppose that is the normal position. So the energy from this point, from the normal, it is increased, it is a decreased amount. So let's suppose how much energy is increased and how much energy is decreased. The total energy, let's suppose the splitting that arises, in the degeneracy, now the degeneracy degeneracy become disturbed. So the energy increased and decreased. The total energy means the total splitting, the energy from that point, from T to G point to EG point, the total energy will be called, the total energy will be equal to del naught, will be equal to del naught. What is mean by del naught? Del naught means energy difference, energy difference, energy difference. Del means difference, energy difference, while zero means that is not zero, that is O, while but we pronounce it that is del naught. So but that is O, and O means that is octahedral. It is used for octahedral complexes, octahedral complexes, for it is used for octahedral complexes. So here, that is del naught, this is equal to del naught. It is called, the del naught is called, the del naught is called crystal field splitting energy. Crystal field, that is very important one. Crystal field splitting energy. Del naught is called crystal field splitting. This is called crystal field splitting. So when crystal field splitting occur, when the degeneracy become disturbed, crystal field splitting occur, means that the EG set orbital, the EG set orbital become the energy of EG set orbital become increased, and when the energy of T to G become decreased. So the total, this splitting is called crystal field splitting, and splitting is denoted by del naught, that is called del naught, del naught. This is denoted by del naught. Del naught means energy difference in octahedral complexes. The energy increase and energy decrease, the total difference called del naught. So, and this energy from T to G to EG, this splitting is equal to 1 del naught. This splitting is equal to 1 del naught in octahedral complexes. This splitting is equal to 1 del naught. 1 del naught is also equal to 10 dq. 10 dq. We can also write that, that is 10 dq. That from T to G to EG, this is also del naught is also equal to 10 dq. And octahedral complexes, crystal field splitting is also equal to 10 dq, which is also equal to 1 del naught, or del naught simply. So del naught, here del naught, the from the normal position to EG, it is equal to the EG splitting, the energy that is increased by EG, increased in energy of EG sector is equal to 0.06 del naught, which is also equal to 6 dq, while the decreased in energy of T to G set is equal to 0.4 del naught, which is also equal to 4 dq. Mean it is equal to it is total equal to, when we add this, that is equal to 10 dq, while this is equal to 1 del naught, which is equal to 1 del naught means is equal to 10 dq. So why the energy of Eg set is 0.6 increased, while uh, usually it should be, when we add this that become 1 del naught and is equal to 1 del naught. So let here there is, this is increased by 0.6 del naught and this increase decreased by 0.4 del naught. Here the ligand interaction to T to G set is very less, so its energy will be decreased less, while the interaction with B will the interaction with EG set, the interaction of ligand with EG set is increased, is more, so the energy of the EG set will be increased more, so that is 0.6 del naught and that is 0.5 del naught, 0.4 del naught. This is also decreased, so we can say that this is the negative sign. From negative we can assume that the negative sign means that is decrease in the energy. That is just symbol, not that is just symbol. This means that the energy is decreased. So and here is also that is decreased 4 times, minus 4 times, 4 dq times. The energy of T to G will decrease from normal to minus 4 dq. This is the splitting of in crystal field splitting in octahedral complexes. Here the crystal field splitting can be defined as the separation of 5d orbitals of the metal ion into two sets having different energies is called crystal field splitting. The separation between these two orbitals, the separation between the 5d orbital, this separation become take place here. So the separation that take place, the energy difference, the energy of Eg and T2G difference in energy of T2G and Eg is called crystal field splitting energy, while the T2G set of energy is decreased by 0.4 time, 4 del naught time, while the energy of Eg is increased by 0.6 del naught times. And that is all were about crystal field splitting. So here is nothing remaining, all is clear now. There this is increased by, this is increased by, this is increased by 0.6 del naught, while this is decreased by 0.4 del naught. This is clear. So these all are about crystal field splitting energy, are these are the application. Octahedral complexes can be applicable, CFT can be applicable to octahedral complex like that, that is T2G set, that is EG sets, EG set, while that is T2G set, T2G and T2G dx by dx that divided, and EG set there is dx square minus 5 square dz square. These all are about octahedral complexes, um, application of crystal field theory that apply to octahedral complexes. Is that clear? This is lecture number 3. I hope you will be clear. So thank you very much. Be careful, be reading books, different books. Okay, thank you very much. Best of luck. Goodbye. Also subscribe my channel, please. It make me feel, it make me happy. Please subscribe my channel. Thank you very much. Share this video with your friend, with your classmates, so that they can also take uh, some advantage from this video like you. So thank you very much. Best of luck. Goodbye.